Source conversion. What essentially this means is that if we have a current source, that can be converted into a voltage source. Similarly, a voltage source can be converted into a current source, and this process is known as source conversion. A source transformation is a versatile technique that can be used to simplify complex circuits. That is, by using this technique, we can reduce the circuit complexity and also make the analysis more manageable. Note that the transformed sources will maintain the same behavior as the original sources. And when we use network reduction technique, this technique will be handy to simplify the circuit analysis. Let's see it in detail. Let us see how to transform a voltage source into a current source. What we have in the figure is a voltage source whose polarity is shown, and there is a series resistor that is connected to the voltage source. The points A and B are open circuited. Then, according to the source conversion theorem, a given voltage source with a series resistance can be converted into or replaced by an equivalent current source with a parallel resistance. So that is shown schematically in the second figure. In the second figure, we have a current source and the resistor has been connected in parallel with the current source. And conversely, a current source with a parallel resistance can be converted into a voltage source with a series resistance. So this is source conversion technique. Let's try to understand how it can be done. Let us consider the case of a voltage source as shown in this figure. And we want to convert the voltage source into an equivalent current source. The first step to do the conversion process is to place a short circuit between points A and B. Now, the current that is flowing in the circuit will be I equal to V over R. Now, we'll replace the voltage source with a current source whose value is given by I equal to V over R, and the resistor will be connected in parallel to the current source. By this way, we can convert a voltage source with a series resistor into a current source with a parallel resistor. In a similar manner, a current source of I and a parallel resistor R can be converted into a voltage source of voltage V equal to IR, to which a resistance R is connected in series with it. An important point that we have to keep in mind when we convert a voltage source to a current source is that the respective open circuit voltages has to be equal and the respective short circuit currents are equal. Let's try to do this problem. Convert the voltage source of 10 volt in the figure to an equivalent current source. In the figure, we have a 10 volt voltage source and a series resistor of 5 ohms. Points A and B are open, and we have to convert this voltage source into an equivalent current source. Let's see how. In the first step, we have to place a short circuit across terminals A and B. We'll place the short circuit and calculate the current in the circuit. The current in the circuit I, the current that is going to flow in the circuit, this will be equal to 10 over 5, and that is equal to 2 amperes. Now we can have the equivalent current source as shown in the figure. That is, we'll replace the voltage source into an equivalent current source, and the resistor that was there in the original circuit in series with the voltage source will now be connected in parallel with the equivalent current source. Now in this problem, a current source has been given and it has to be converted to an equivalent voltage source. In the figure, it is a 5 ampere current source and a parallel resistor of 2 ohms has been connected. We have to first find out the open circuit voltage across terminals A and B. The open circuit voltage VOC, this will be equal to the potential drop across R. And the potential drop across R is simply I multiplied by R, that is equal to 5 multiplied by 2, and that is 10 volts. Now what we will do is that we will replace the current source with a voltage source and we'll connect the parallel resistor in series with the voltage source. So this is how we convert the current source to an equivalent voltage source. Another problem, use source conversion technique to find the load current IL in the circuit. If you inspect, you can see that there is a 6 volt voltage source and then there is a 3 ampere current source, and RL is a load resistor that is connected in the circuit. We have to find out IL, which is the current that is going to flow across the load resistor RL. Let's see how it can be done. In the first step, what we'll do is that we'll convert the 6 volt supply, which is in series with a 3 ohm resistor, into the equivalent current source. For that, we'll take the 6 voltage supply, which has a series resistor of 3 ohm. So this is 6 volt 3 ohm, and then place a short circuit across these two terminals. Now there is a current flowing in the circuit which is given by 6 divided by 3, that is equal to 2 ohms. In figure B, the 6 volt source with a series resistor 3 ohms has been replaced by a 2 ampere current source and a 3 ohm parallel resistor. So that is shown in this figure. And when we analyze, we can see that the 3 ohm resistor and the 6 ohm resistor are in parallel. Now we can find out the parallel combination of 6 ohm and 3 ohm resistor, and that is given by R equal to 3 multiplied by 6 divided by 3 plus 6, and that is equal to 18 by 19, which is 2. And when we simplify the circuit, it will be like this. That is, we have replaced the parallel combination of 3 and 6 into an equivalent resistor R dash having 2 ohms resistance. Now we have to again simplify this figure. But when you inspect, you can see that the two current sources 2 ampere and 3 ampere cannot be added because of the presence of this 2 ohm resistor in between. In order to simplify this circuit, what we'll do is that we'll convert this 2 ampere source with a parallel 2 ohm resistor into an equivalent voltage source. For that, we have to consider this circuit. So this is 2 ampere, and then we have a 2 ohm resistor, and we'll keep this as open circuited. So this is A and B. Now we have to find out the open circuit voltage, and the open circuit voltage is given by 2 amperes multiplied by 2 ohms, that is equal to 4 volt. Because as the total current comes to this node, it flows only through the resistor 2 ohm because the points A and B are open circuited. So the entire current flows across the resistor 2 ohm, and there will be a potential drop across the resistor, and that is the same potential that we will see across points A and B. So now we have replaced the current source into an equivalent voltage source 4 volt in series with 2 ohms. So that has been done in this figure, where the 2 ampere current source with a parallel resistor 2 ohms has been replaced by a 4 volt voltage source in series with a 2 ohm resistor. Now we see that these two resistors are in series and that can be added, further simplifying the circuit. When they add, the total resistance will be 4 ohms. That is, we have simplified the circuit to 4 volt in series with 4 ohms, and then the current source, the 1 ohm resistor, the load resistor RL, 3 ampere, 1 ohm, then RL is 3 ohm. Now we are in a position to simplify the circuit again. We'll convert this voltage source in series with a 4 ohm resistor into an equivalent current source. So we have this 4 volt source which is having a series resistance of 4 ohms, and we'll take these 2 points open circuited, neglecting the other part of the circuit. To convert that into an equivalent current source, we'll connect a short circuit across the 2 points. Now the current that is going to flow in the circuit is simply given by, this is 4 ohms, 4 divided by 4, that is equal to 1 ampere. That is, this part of the circuit can be replaced by a 1 ampere current source and a parallel resistor of 4 ohms, and that is shown in the next figure. So we have converted the circuit into one which is having a 1 ampere current source and a parallel resistor 4 ohms. It is now possible to add the two current sources and then combine them into a single 4 ampere current source as shown in this figure. So the 1 ampere and the 3 ampere has been added, and the total current in the source is now 4 ampere. So we have simplified the circuit from this to this, and now we have to find out the current that is going to flow across the load resistor RL. For that we can use the current divider rule. Let's see in brief what current divider rule is all about. Let us assume that we have a current source which produces a current I. That is, the current that is there in the circuit is I, and when it reaches this node, it divides into two, that is I1 which is going to flow through a resistor R1 and I2 which is going to flow through resistor R2. In that case, according to current divider rule, the current that is going to flow through resistor R1 will be equal to total current multiplied by resistance in the other branch. So that is R2 divided by the total resistance in the circuit, that is R1 plus R2. Similarly, I2 is given by the total current in the circuit multiplied by resistance in the other branch. The current is flowing across this branch, so this is I2, but we are considering the resistance in the other branch, so that is R1 divided by R1 plus R2. So this is what current divider rule says. Now we can apply the current divider rule into the circuit that we were analyzing to find out the current across the load resistor. The current across the load resistor is total current. The total current is 4 ampere multiplied by the other arm consists of a 4 ohm resistor, so that is 4 divided by total resistance in the circuit. So the total resistance includes 4 plus 1 plus 3, and this is equal to 4 multiplied by 4 divided by 8, which is equal to 16 by 8, and that is equal to 2 amperes. So the current that is going to flow across the load resistor would be 2 ampere. We shall now explore the concept of ideal constant voltage or ideal constant current sources. To understand the concept of ideal constant voltage source, let us consider the figure that is shown here. In this figure, we have a 6 volt supply which is having an internal resistance of 0.005 ohms. Across terminals A and B, we will connect a load resistor RL, and the output voltage can be measured across the load resistance RL. A resistor with an arrow like this indicates that it is a variable resistor. That is, the value of RL can be changed. As we change the value of RL, we can see that the value of load current will also change. That is, as RL increases, IL will decrease. And we define a constant voltage source or generator as one whose output voltage remains absolutely constant for whatever change in the load current. That is, when we change the value of the load resistor RL, the load current will change, and even if the load current changes, the output voltage VO remains almost the same. And that is a concept of an ideal voltage source. For a voltage source to be ideal, it must possess zero internal resistance. The internal resistance that is shown in this figure is 0.005, which is very low, but ideally it should be 0. If it is not equal to 0, then there will be a finite potential drop across the internal resistance, and in that case, the output voltage provided by the source will not be constant. So if the internal resistance is equal to 0, the output voltage provided by the source would remain constant irrespective of the amount of current drawn from it. Practically, such an ideal constant voltage source cannot be obtained. However, we can make a near ideal constant voltage source by making the internal resistance as close to 0, that is, with a very low value. Now let us demonstrate the working of an ideal constant voltage source with the circuit shown. In this circuit, we have a 6 volt battery that has an internal resistance of 0.005 ohms. If there is no load, that is, when it is open circuited like this, the output voltage will be constant, and that will be equal to 6 volt. In this case, no current flows through the circuit because it is open circuited. Now let us assume that we connect a load resistor across A and B. When we connect a load resistor, the load current increases. Let us assume that the load current increases to a value 100 ampere. When the load current increases to 100 ampere, the potential drop across the internal resistance of the cell is 100 multiplied by 0.005, which is equal to 0.5 volt. Now in this case, the output voltage will be 6 minus 0.5, which is equal to 5.5 volt. That is, with no load, the output voltage is 6 volt, and with a load resistor connected, which permits a current flow of 100 ampere, the value of the output voltage becomes 5.5 volts. Note that we have made a wide variation in the load current from 0 to 100 ampere, and in this range the voltage only changes from 5.5 to 6 volt, and we can consider this as almost a constant voltage source. Now the case of an ideal constant current source. Let us consider the case of a voltage source which is having a very high internal resistance. In the figure, a 6 volt supply has been shown which is having an internal resistance of 1 mega ohms. Across terminals A and B, we are able to connect a load resistance whose value can be changed from 20 to 200k. By definition, an ideal constant current source is a voltage source whose internal resistance is infinity. As an internal resistance of infinity cannot be realized in practice, a source with very high internal resistance as compared to that of the external load resistance can be considered as an ideal constant current source. Let us try to understand the working of an ideal constant current source with a bit of mathematics. So in the figure, we have a 6 volt battery or a voltage source that has an internal resistance of 1 mega ohm, and we can change the load resistance RL from 20k to 200k. Essentially, as we change the load resistance, we are actually changing the current that is flowing through the circuit, that is a load current. Let us assume the case when RL equal to 20 ohm. In that case, the current in the circuit is I dash equal to 6 volts divided by the total resistance, that is 1 mega ohm plus 0.02. So the unit is mega ohm, and this is equal to 6 divided by 1.02 microamperes, which is equal to 5.9 microamperes. Now let us make RL equal to 200 kilo ohm. When RL equal to 200 kilo ohm, the current that is going to flow in the circuit is 6 unit is volt divided by 1 plus 0.2. So this is resistance whose unit is mega ohms, and therefore this is equal to 6 divided by 1.2 microamperes, and this is equal to 5 microamperes. So the load resistance initially was 20k, and then it was increased to 200k. That is, we have increased the load resistance to 10 times. When we increase the load resistance 10 times, we see that the current decreases by 0.9 microampere, so which is a very low value. That is, even for very high values of the load resistor, the load current remains almost constant. Thus, this source with a very high internal resistance can be considered for all practical purposes to be a constant current source.